So today I'm going to talk about understanding of an executable binary. So most of the audience, I heard that you guys are either junior or a senior, right? So it's pretty much possible that you have not seen an executable binary inside if you are not very interested in executable binary itself, because it's likely that you have you know created your program with a high level languages like C programming or C++ or Python interpreter language, right? So these are the high level languages, human readable languages. Once you write the code with those languages, then you can interpret the code or you can compile the code, and then finally you get the executable binary. But once the binary is created, you don't need to take care of what's within. So that's why I decided to show you what what it looks like as an executable binary. It definitely consists of zeros and ones in the slide like this. So let me start with the birth of an executable binary. So every software, particularly distributed software, uh, is at a form of an executable binary, right? So when you download, suppose you download Chromium browser, and you can run this browser by double-clicking the downloaded version, right? And this is an executable binary. When you run the binary, then your operating system naturally run a process. You run a file, then operating system allocates a virtual memory space for that program, and it creates a process and allocates a virtual memory space on behalf of you. So, uh, as I said, we have dealt with human readable source code like C and C++, and the thing is that so we have to translate this language, the source code, into a machine interpretable machine instructions. And the language that the machine can understand is an assembly language. This is totally different language from the source code language like C and C++. So, so assembly um, is generated by an assembler, and that's the sort of the last component of compiler. And this translation process is called compilation. And the compilation is done by a compiler toolchain. This is what we know, right? And the final product of the compilation is an executable binary, and executable binary has the code instructions, machine instructions, as an assembly language. So now we know the compiler toolchain produces machine instructions as a final product after a complex compilation process. So suppose that we have a file here, and inside there there is assembly code, machine instructions, and an executable binary is a stored file in a disk. And an executable binary has a specific format for running. So for running means for executing. Now, can we somehow understand the machine instructions? How? Because it consists of zeros and ones. You cannot interpret it as it is. we have to disassemble this machine instructions so that um, it could be somewhat human readable. And disassemble the code uh, can be done by a disassembler, and this is called the disassembling process. And disassemble instructions. The assembler languages may vary depending on a computer architecture because different computer architecture speaks different languages. So for example, Intel x86 has its own language, and this is called instruction set architecture, or ISA. And ARM PowerPC MIPS, these are different architecture, which means ARM has its own language. So if you have an executable for running under x86 machine, then ARM architecture cannot understand what you are talking about. So x86 executable cannot be run under the ARM or PowerPC architecture because of the language. Now you have an executable binary, then who can run it? Yeah, you can run it, but on behalf of you, operating system runs the executable binary. What you do is to double click the binary that you are using Windows or any GUI, graphical user interface environment, then you double click it mostly, then an executable binary would be running. So here there are two different views. One is this executable binary is stored as a file on a disk. That's the first part here. So this is stored as a file. Once you run this file, then operating system creates a process. So this is the process, and operating system will allocate this process own memory, virtual memory address. Why is this called virtual? Um, because operating system allows you to run multiple processes together at the same time, right? And each process has its own memory space, memory address. So from a process perspective, it doesn't recognize that there are another process outside. It has its own virtual memory address. Suppose that you are running a 32-bit machine, then each process has 2 to the power of 32 bits, size of virtual addresses, which is almost 4 gigs, right? Exactly 4 gigs. And when you here as a file, there is a specific region for machine instructions, and when a process is generated in memory, we have a specific region for this machine instructions as well. And this process is called mapping. And this mapping as a file and as a process, we have totally different views. Let's look at this. As I said, we have totally different views. One is file view and another one is process view. And if your executable file is stored on a disk, then each different region is called a section, and in memory each different region is called a segment. In a process, a different segment typically has a different permission. So for a segment, it's very important to determine if this segment requires which permission, like readable permission or executable permission. So let's deep dive into compilation a little more. So we have a multiple source code. Uh, think about the C code. Maybe you might have a single source code, but it's typical to have multiple source code. And the compilation process have n different source code. It actually converts the source code into an object. And this is compilation process. At the end of the compilation, there is an assembler. An assembler produces the machine instructions, and inside the object file there is a machine instruction part region. Once the object files are generated, a linker consolidates all the object files together to generate a final executable here. So here a compiler generates an object file in an executable format, and then a linker combines all the object files together to produce a final executable. And this is how we get the executable. And compiler compiles the source code to produce an object file. Linker, links all the object files. And if a library is required inside executable, then a linker actually links an external function in a library if required. And a library, as you know, is a set of common functions to be exported. So the library has a sort of the interface that could be exported, like function 1, function 2, function 3, like this. And then executable can import these functions, and we have the interface, right? Actually, a compiler has different processes. Like if you have the source code, then preprocessor. If you think about the shop, include the standard input output that had which usually comes first at the first line of your C code, right? And define a certain variable there. Then a preprocessor preprocesses this, including thing, beforehand. And lexer and parser both creates AST or syntax tree, and then the compiler produces the intermediate representation here, or it's called IR. Once the compiler generates the IR, then the optimizer internally optimizes this IR. So this is a very important concept, because the reason why compiler produces intermediate representation is it wants to have independent backend from front end. So once you have the intermediate representation, then the only thing left is to produce the final executable by selecting an instruction depending on the architecture, right? That's what the instruction selection phase does. That's what the assembler phase does. So largely, a compiler toolchain, I have to say toolchain, I think compiler itself will do, consists of front end. So before generating intermediate representation, until optimization. This is called the front end. And instruction selection phase and assembler phase, these are called back end. And as I said, compiler generates intermediate representation, which is independent from an architecture. And there is another optimization at the back end, but it's not important for now. So as I said, compilation process looks like this. We have source code, right? And with a transformation process by compiler, it produces intermediate representation, and this part is called the front end. And at the back end, we have assembly process, which converts intermediate representation into machine instructions. And we can reverse this process. And as we saw in the previous slides, we can disassemble machine instructions because these are zeros and ones, so that it's pretty hard to recognize what they are. So we have a disassembly process by disassembler, and then we get the somewhat human readable and disassemble the code. Can we go back to the source code from the machine code? And the answer is partially yes, by going back to the source code from the machine instructions, and this process is called decompilation, and this can be done by the compiler, but this is really hard process, and it requires a lot of processing. So first, all the decompilers produces intermediate representation first from the machine code, and then from the IR it attempts to generate source code. And this process from the machine instructions to intermediate representation by decompiler, this is called lifting process, and this process is done by a lifter. And when you get the source code from the machine instructions, and this is totally different from what you expect. It's not the machine code, I mean the source code you have written, because machine instructions do not have much semantics. It does not have much syntactic information as well, because during the compilation, everything has been gone, right? As I said, compilation is highly destructive logic process. So in the source code, you can find these, uh, you know, um, this kind of information, including function names, function signatures, data structures, variable names, class hierarchies. If you are writing your code in C++, right, you have the class and its own hierarchies because of the inheritances and so on. And you have types and comments written by a programmer. But after compilation, if you get the binary code, everything here is gone, right? Inside binary code, there's nothing. So we have sort of the disassembly and decompilation process to roughly understand the behavior of binary. And this behavior is sometimes called binary reversing. Here, reversing stands for reverse engineering. So this is sort of the other way around, right? Compilation is the transformation from source code to the binary code, but binary reversing is sort of an attempt to understand the binary code by reverting from binary code to source code. But the source code that you can obtain here is pretty much different from the source code that you have written. Okay? Because all the function names are gone, all the function signatures gone. You can just make an inference, right? Types are gone, but you can infer the types. The variable names are gone. You can infer somehow, but it's pretty hard to infer the variable names and function names in particular. And here, if you produce a binary code with a debugging symbol, then most of the here information but comments are available because is um, debugging symbol contains the debugging information for debugging, right? So it actually contains the function names, data structure, type information, and so forth for debugging purpose. And it actually contains the line of code as well in order to refer to the source code. But usually the binary, an executable binary, has a stripped of these debugging symbols. So this information is unavailable. So the building blocks for binary code internals. These are, uh, important building blocks to understand binary code a little bit more. So instruction, this is the one that you saw in previous slides. Basic block and function. Here the function is the binary function, which is slightly different from the function that you define in a source code, but similar. And we are going to look at execution flow and see other construction for the binary. So instruction. So an instruction is defined in a set of machine language for a certain CPU. And instruction set architecture, or ISA, has predefined these machine language machine instructions. And for example, Intel x86 instruction set architecture, it has two different parts. One is opcode and the other one is operands. It has a single opcode and 0 or more operands. So operands are optional. The size of instruction is variable, and we say Intel ISA is a variable length, meaning that uh, there is a 1 byte instruction and up to, if I remember correctly, there is a 15 bytes instructions as well. So the length of each instruction is not fixed. Alright, what is a basic block then? Basic block is a sequence of instructions that could be executed in order. So this is an important part. So every instruction inside the basic block should be executed in order, sequentially. This means that there is only a single entry point and there is a single exit point per basic block. So it means that a branch instruction like jump instruction, these instructions cannot jump into any instruction in the middle of basic block. It always guarantees that your jump instruction should jump into the entry point, and execute the instructions inside page block in order, and then you can exit to the exit point. So that's why oftentimes page block ends with unconditional or conditional jump instruction. So if jump is not equal to, then it jumps to another page block. So this page block can be, end with a jump family instructions. And if page block does not end with an instruction that controls a flow, then the following page block is called a fall through page block. Why? Because this page block ends and you just fall through and you go to next page block. Say if you're true here, if it's the false, then you go to another page block. So here basic means a basic execution unit that control flow enters or exits. Okay, and a page block consists of one or more instructions. And what is a function? A binary function consists of one or more page blocks, and here a function is often regarded as a logical unit of a certain task. This is pretty similar to the function you write in the source code, and this is interchangeably called a routine, subroutine, or a procedure. And a function may not correspond to the user-defined function because you define a function f and g, but during the compilation optimization process, it may perform function inlining. So what is function inlining? A function f can be part of another function, so the function goes inside g without the name here, and g actually embeds the function f. That is how the function inline does. Why this is happening as an optimization? Because when you invoke a function, it has a quite large overhead, like a function prologue or function epilogue. There is a series of processes to invoke a function. So that's why in order to keep the better performance, sometimes the compiler optimization uses the technique of function inline. There is a function splitting as well, but it's not happening very often. So um, um, optimization tries to boost the performance, and if you look at the binary, the function boundary, where is the starting point of function, where is the ending point of function, it's sometimes it's blurred. So that the function binary function identification itself is an open problem or as a research problem. Execution flow, here control flow graph. So execution control flow graph is the intra-procedure execution within a function. As I said, the basic unit of an execution flow is page block, and the order of the page block is executed. And control flow graph is a directional graph. So from one page block, you go to another page block, it has a direction. And if you draw a graph with a vertex and edge represents a flow, and whereas the node represents a page block. And sometimes page block cannot be reachable, which we call that this is unreachable, and this is called orphan page block. And page block may not be determined statically, but reachable dynamically at runtime. So what this means is you cannot analyze your program statically all the time. because sometimes at runtime uh, the reachability can be determined. For example, if you insert a certain input, then depending on the input, the reachability of basic block can be determined. That's why we call we say that the reachability of a basic block is non-deterministic. Likewise, a call graph. Call graph is intra procedure, which is pretty much similar to control flow graph, but the unit is function call. And the execution is done between functions, and we can similarly draw a graph with the vertices of node and edges of call invocation, and by with a callee and caller we can have a directional graph. Just like a control flow base block, we may have an orphan function, and the function may not be determined statically but reachable dynamically with the same region, and we say that reachability of function is non-deterministic. There are other constructions like a jump table or v-table, but let me skip this part. All right, let's demystify an executable format. We already checked out the file as an executable, right? And an executable has its own format, and particularly in Linux or in any kind of Unix operating system, it follows the ELF format, which stands for executable and linkable format. That's why we call it ELF like this, and it has its own structure. So first, ELF has its own program header, and as I said, as a file, the regions are called section, and each section has its own section header. An ELF structure has been defined. Here, it has its own specification. An ELF structure is for three main types for object files. One is a relocatable file, and another one is executable file, and shared object file. Shared object means library, dynamic library, and executable file is the the main executable like bin ls. Object file is the relocatable file during linking. So these are the main types. And what are the how is the structure defined? We already have the agreements on that with the specification. Everything is based on agreements in computer science, protocols, symbols, definition, standards, terminologies, and specifications. So particular, we have the specification for ELF. So we have ELF header as a file. So using the lead-elf utility, we can get ELF header. It automatically parse the ELF header with H option. It's very simple. You can get the entry point address. So this is the exact address when you run a program. The first instruction to be executed is the entry point. And where is the start of the program header? When is the start of the section header? This is the offset of the file, and something like that. And we have the ELF sections. So with ELF utility, using the large S option, then you can get section headers. It automatically parses ELF sections, and section header, as we have 28 different sections, it has 28 section headers, and each section header contains this type, address, offset, and size, and flags like this. And one thing that we should um, look at is the flag here. So inside the section, and each section has its own flag, and A means allocatable, and X means executable, and W means writable. So these sections has the writable permission, where this section has the executable permission. And most of the sections that has the executable permission contains the code, and PLT section itself has some code, and text section is the section for code, um, and so forth. And these are the writable permission, contains the writable permission. And how do we parse these headers? As I said, it has been defined in a specification. And if you look at the specification, the file header has been defined with this struct elf32 elf header, and this is another struct for section header. So elf32 section header SHDR, right? So if you look at the struct, then all the different fields are predefined, and you can parse it with the utility. And similarly, these are segments. So now you know what's the difference between sections and segments, right? Sections is for the file, and segments is just for process. So the most important thing you remember in segments is the permission. So with the same utility read up with the small letter L option, you can get the segments of an executable like this. So here we have the virtual address and memory size. So for example, here the first load has the 40000, and the next load is 40100, which has the executable permission here, right? Uh, the second load would be this one, which has the executable permission that contains init section, PLT section, text section, and finish section. These sections contain the code, so that's why we have the executable permission, and we have the readable and writable permission for here. For other sections, I guess that's for the dynamic, and in array this GOT, PLT this section, and it actually requires writable permission for this too. So depending on the permissions, we have the segments in a virtual memory address for a process, right? Now we have a symbol, and programs symbolic different. It actually has the programs symbolic definitions as references, and it's defined in a symbol table, and a symbol table consists of symbol entries. It includes types, bind information, name, and so forth. Usually, symbol information is not available, but there are several symbol tables that should be included. One is the DYN sim or dynamic symbol, because these symbols are not defined. So here UND means undefined. So we are going to use the printf function at glibc. Libc is library function. So instead of having this code inside this particular executable, this executable is going to borrow the, this function printf or puts from the library, which is glibc in this example. So dynamic symbol section contains all the different kinds of symbols that should be imported from a library. So you should not remove this symbol section. And relocations, it's a process of connecting symbolic references with other definitions. Um, like other sections, relocation table can be parsed uh, per relocation entry, including an offset and a type. The relocation also has the structure predefined in the specification. Um, so here, relocation is um, required. So for example, if you think about the object file here, let's say 1.0, 2.0, and then when you combine this file uh, 3.exe, then 1.0 has its own, it actually uses a function f, which is defined in 2.0. Then at the very time of 1.0 compilation, it doesn't have the information, the location information of f, because the function f is defined in a different object file. At that time, a linker will, you know, reserve this issue. That's what the relocation is for. So when 1.0 is produced, 1.0 contains relocation information. Let's say f is somewhere, and when f is reserved during the linking time, then the b.exe is no longer having the relocation information, right? So relocation is sort of a placeholder that should be reserved later on. If a relocation is inside executable, that means it actually imports a function from a library. And what is a struct library? Binary. Oftentimes, symbols and debug informations are unavailable in real programs because it can reduce the size of a program. You can avoid the exposure of the program. Function names, variables. You don't want to, disclosure this information to others. And we have the strict utility that does the job, which removes symbol table, string table, and all the sections pertaining to debugging. But as I said, it remains the dynamic symbol information, including din.sim, din.string, letter din, dynamic sections. Otherwise, you can't import, required functions from a third-party library or any library that is required by an executable. And in general, a binary analysis is very difficult when debugging symbols are struct off. But we mostly deal with the struct binary in a real life. Okay, we're almost done. Let's talk about the linking and loading as the final uh, topic. So recall the compilation process. So we have source code. It generates IR, produces object files. The linker generates a binary executable. And library is a collection of resources readily reused by other programs. And it offers well-defined interfaces. If you think about the API as exported functions. And there are two different libraries. One is a static library and the other one is dynamic library. And static library can be obtained at compilation time. You can get the archive format as a static library. In the Linux system, you can see the file extension .a and just as combination of all the object files. And in Microsoft Windows, the file extension is lib, and dynamic library can be loaded at load time or run time. And the format of dynamic library is ELF in Linux system or any Unix system. But in Microsoft Windows, the format is PE or portable executable. We haven't talked about this, but anyway, so this is sort of another format that is used in Windows. And the file extension is SO in Linux and DLL or Dynamic Link Library in Windows. So static linking is a process of linking a subroutine statically. So during compilation, a linker seeks all required routines. A routine means functions. It is performed by a static linker, and in Linux, LD is static linker or Gold is a static linker. You know, they are the same, but Gold supports the parallel computing, parallel linking. And as I said, the file extension is .a in common. And static linking is straightforward, but we have two drawbacks in terms of efficiency. Because it requires recompilation for code updates. So if you think about the bug fix, right? And let's say we have a .a file. As I said, .a file has different object files, say 1.0, 3.0, 4.0. Say we have 4 different object files in a single .a archive as a static library, then if an executable requires any function in 2.0, then it actually grabs all the object files and it should be part of the final executable. So what does this mean? If any function in 2.0 has been updated because of the bug fix or whatever, then you need to recompile the source code to get the executable. And every program, if you use this archive, then every program has redundant library, and it contains a copy in its executable, which is a waste, right? And this is steady linking process, and each object has a different one, and each object has its own section, and in the layout during the linking, all the text code are combined like this, and finally you get the text, right? Other sections are similar. So this is a linking example, but let me skip this part. And finally, dynamic loading. Dynamic loading is also known as dynamic linking. So dynamic loading is equivalent to a dynamic linking. It's a process of finding a subroutine at load time or runtime, because you cannot find the function that should be borrowed at compilation time. You should utilize a specific function from a library at runtime or load time. And this is also known as a late binding, because you should wait until load time or runtime to obtain a function in a shared library. I think we already have done the file extension before. Okay, I think this is pretty much it. And so far uh, in this course, in this class, I talked about an executable file and what is the format like, and we also talked about static linking and dynamic linking and dynamic loading, right? So I hope you guys to help understand an executable a little more. If you haven't looked at previously, hopefully this helps you understand software binary, executable binary better. And thank you very much for your attention. And if you have any question, then please email me. Thank you. Bye.